So guys, this is where everybody should have the same answers.
Really, for real?
Huh?
That's nuts.
Yeah, it's a new chart, but we know how to read two other charts. The third chart is going to be easy to get to understand, I would hope.
You're going to get to see the square. Alright, so, but what is the hope?
Alright. So, obviously, I don't know how you guys have grouped up or not, but whoever's actually done their own data, you're going to have different answers than everybody else. So I'm just going to show you the data I did. And the process is the same for everybody, just with your data. So I picked those numbers, see them? And then I got a mean of this. I got a sample variance of this. I'm kind of doing this on purpose because the book can be evil and give you variance or standard deviation, so you have to be very aware of what it is you have, the number. So you don't want to square a variance, because that's like S4th. Holy shit. Right? So in this problem we had S and sigma, that's why we squared both of them. But now I've got, oh yeah, you guys, I don't think it works over there, it's too bad. Now I've got S squared here. And I'm comparing it to, what's my claim going to be? What's my claim? Yeah, sigma equals 13.374. So where's that go? The hope. So what's the high? That's crazy. So that's why I got you part C. I wanted you to find the chi-square big chi-square small, because that would be a two-tailed test. So now I've got my rejection region set up. If chi-square is smaller than that, it's going to be in this rejection region. If it's bigger than that, it's going to be in that rejection region. The numbers are different than we're used to. We're used to having a negative and a positive, but beyond that, that's exactly what we've always done. Right? That's a two-tailed test. It's got to be out there. Let's see. So for me, my chi-square, I got, let's see, 31 times S squared was 287.237 for me. And I'm going to compare that to sigma squared, which sigma would be 13.374 squared. You stop there for a second. I did already. That's how I got the variance, was I squared it. See, that's part of the reason why I did this. Yes, I was purposefully evil because the book can be evil too. You have to be very aware of what the number that you're looking at is. So this one I'm not going to square because it's already the variance. This one I've got to square because it's only the standard deviation. Alright, I like it. You guys either like it or just can deal with it. Cool. And then if you do this, I love all this room. I can't deal with it. Blah, 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 blah. So if I do this, I know you can't see this. You can see it over there. Hey, look, this side of the room. You got stuff to look at. So I got 31 times, what is it, 287 for me. Point. So the only difference between me and you should be the number I just put in. These other numbers should be the same. So for me, I got a chi-square of 49.783. So I look back here, so mine is 49.783. I would be in the rejection region. I would reject the hope. I would support the high. And of course, my claim was the hope, so I would say I have found enough evidence to reject the claim that the standard deviation is equal to that. You guys semi with me? All right, now let me see. Did everybody get to that step yet where you figured out if you failed to reject it or reject it yet? You guys gotten there yet? So the only difference, if you haven't done this formula yet, you put your variance here. That's the only difference between you and me. I got a different variance. You put your variance there. Has everybody done that now? Nobody's really moving at all, so I'm going to assume that you've done that already, or are you just going to pretend like you did? Cool. How many guys failed to reject? That's weird. How many guys rejected? How many guys
I reject.
don't like to raise your hand? All right, you're weird. You just raise your hand. To be honest, this is kind of neat. The actual standard deviation is this. I'm sure you guys are used to that by now. That is the real standard deviation for all of these data points. So I rejected that claim that it was equal to that, and that turns out to have been wrong. It's not that it did anything wrong. That's the built-in thing with statistics, of course. There's always a chance that your answer is not going to be right. We're never going to know if we're right or wrong. We just know the probability that we're right or wrong. All right, this is a two-tailed test. Alpha was what?
0.10.
So there's a 10% chance. 10% of the time when I run this test, I'm going to get it wrong. So 10%, roughly 10% of everybody who ran this test, roughly. That's only an average, right? We're kind of a small sample, but roughly 10% of us should have gotten that wrong, should have rejected it when really we should have failed to reject it. So what kind of error is that, just to throw this old thing at you? If I reject a true null? Type 1, the smaller phrase, rejected true null, rejected true, that's type 1. Fail to reject a false, the bigger phrase, that's type 2. I'm not really that interested in that anyway. Yeah?
Can you briefly go over how you got expert data?
Oh, sure. Could I see somebody give me back one of my copies of the chi-square?
Yeah, here you go.
No. Oh, thank you. And let's see what's over here. So if you draw the picture, it'll be a little bit easier, but also what's really nice is there's a two-tail test. Alpha is 0.10. So how much area would there be in that upper tail? 0.05. So I'm going to look at 0.05. The minute, if I need both tails, if I look at 0.05 for one of them, I'm going to look at 0.95 for the other one, because the two things I look at have to add to be 1. Are you guys with me? If I look at 0.10 for one side, I'm going to have to look at 0.90 for the other side, because they have to add to be 1. So I'm getting the whole picture. Maybe. All right. It's nothing earth-shattering, so I don't mind the non-reaction. So if you look at 0.05, and degrees of freedom here would officially be 31, but our table sucks. We don't have a 31, so we just go to 30. So I go in this column, I go down, stay in the column, Jeff, until I get to 30. There it is, 43.773. That's the upper bound. That would be like 1.96, and the lower one would be like negative 1.96, but z-scores go negative, chi-square scores don't. That's why they're a little bit weird. So if I want to find the other one, I just look in the same row in the 0.95 column. Because again, please, I don't like stopping there. If the chart says it's the area to the right, that's how you find a chi-square. So that's why I look at 0.05 first. That'll be this dude, right? That's the one I call a chi-square big, because he's the big one. And what's to the right of this tail? Well, what's in this tail? It's got to be the other 0.05, right? So it's got to be the right to it of it, 0.95. That's why these two have to add to be 1, because that is what this would be. They add to be 1. So it's nice to know the rule and they add to be 1, but never forget why that's true. It's not just because we said, well, that would make it easy, let's do that. No, it's what actually happens. It's what physically happens. Oh, real quick. Let me find the other one real quick. So if we go 0.95, we go down to 30. There's the 18.493. Right, that was chi-square small. Cool, I like it. That's how I found those. And they act just like negative 1.96 to 1.96. A number you should know. Negative 1.645 to 1.65. They do the same job. I'm sorry, so what's your... We have not found sufficient evidence to, in this case, reject the claim. Well, the one we're doing was equal. We have not found sufficient evidence to reject the claim. I want you to understand, that last step is exactly the same. Exactly. There's nothing different about that last step. Did you get in there? You found evidence to do something. Did you not get in there? You didn't find evidence to do something. To do what? Whichever one of these your claim is. You didn't get in there, you failed to do one of these two things, depending on what your claim is. It's exactly the same as it was for Chapter 8 and Chapter 9. Yeah. That's confidence intervals. So we can do a problem like that right now if you want to. All right. Yes.
So if the number that we got, like, the region,
What'd you get?
I got 31.45.
So it wasn't bigger than the
The-
40, whatever it was.
Yeah.
So you failed to reach it.
Okay.
Which, as it turns out, we know is the right answer.
Yeah.
In real life, you don't know. You just know there's a certain chance you're wrong. Do you see what I'm saying? So if it was bad to reject it when it was really true, if that's really bad to reject it, I should have made my alpha smaller, so I would have made that happen less often, right? But I made my alpha 10%, so 10% of the time I'm going to reject it when it's really true. So it all depends on how bad that mistake is. You can control that, how often that mistake's going to happen. You can control it. If you make that mistake happen less often, then the other mistake, the type 2 error, is going to happen more often. Oh shit, you got to know which one's worse. Okay, maybe. All right, anything else about that? All right. This guy's like, I had no idea Stats got this awesome. The real unfortunate thing is, and some semesters I barely even get to chi-square, but Chapter 11 is some really cool shit, but it's just too much to try to really totally get into. But this is where you can truly test to see if something's normally distributed. Or you can truly just directly test to see if this thing causes this thing. And then you can get into multiple variable tests. You have like 5 different variables you're looking at, and you want to see which one has the most effect on something else. It's crazy. That's the next kind of layer to this. That would be a Stats 2 course, getting into that kind of stuff. Unfortunately, we don't offer Stats 2. All right, so let's do this. We'll do a confidence interval problem with chi-square, and then we'll see if there's any left over you guys want to talk about. Make sure that you get a practice final before you leave if you didn't get one. Let's see. Let's just use this here. Shy and shy. One seed shy T. Yeah. Thank you for letting me find that word. Alright, so let's see. Let's make up some more numbers and see what happens. Alright. Take a sample. What you got, Jeff? 51. 51 dogs. Alright guys, so we take a sample of 51 dogs. Just gotta roam around and find some ducks, right? Somehow, I'm not gonna get into the specifics, but somehow we know how long they're gonna live. I have a sidekick with me. So we know that we find a standard deviation in their lifespan of 8.019. So maybe this is a longitudinal study, so I'm watching these dogs over time. And I know the standard deviation in how long they live is that many years. That seems kind of much, Jeff. Oh, screw it. Just go with it. I like it. Make sure the tortoise is in. So find the, up there yet, 98% confidence interval for the true standard deviation of the dog's ages. So we take a sample of 51 dogs, we find a standard deviation in their lifespan of 8.019. Find the 98% confidence interval for the true standard deviation of dogs' ages. So for the population of dogs. So remember, just like Z has a formula to it, chi-squared has a formula to it. That's the one we just used. N minus 1, S squared. Squared. So if we want to construct a confidence interval for sigma, and I want to point this out. Here's the z-score formula, right? Become a sigma. There it is. And if I want to make a confidence interval for, let me make this the mean there. If I want to make a confidence interval for the mean, I'm going to solve for the mean first. I want to see what the formula is for the mean, and then I'm going to go plus or minus, up or down. That's how we came up with the formula for confidence interval for that. So I solve for x bar, and that's where I get mu plus z sigma x bar, right? We make that plus or minus, so we go up and down. You guys kind of with me here? So here, this is even easier. I want to make a confidence interval for a coverage interval. I want to desperately make a confidence interval for the population standard deviation, so a variance. So I'm going to solve for it. Let's kick ass. All I have to do is. So then I get, just like this has that plus or minus. Why is that plus or minus? Why is it so easy for z-scores? Stupid z-scores. Why are they so easy? The other one's there, the other one's going to be exactly the same distance over there because the normal distribution is symmetric. Right? We have the freaking chi-squared, dude. It's too bad for us. So I solve for sigma squared and I get n minus 1 s squared over chi-squared in general. But just like we do here, I want to make it upper and lower bounds for this thing. So then I say that this is the lower bound, and this is the upper bound. Again, it just makes sense. When you divide by a big thing, you get a smaller number. Divide by a small thing, you get a bigger number. That's why it makes sense that they are where they are. Makes more sense to me than left, right. And oh yeah, you put the right one on the left side. Oh shit, screw that. I don't like that. So we have n, we have s, right? So what's the only thing we're missing? There are two things. Chi-square big and chi-square small, yeah. And how am I going to get that? What's going to tell me how to find it? Yeah, so we have degrees of freedom is 50. And what else tells me how to get it? What's alpha? 0.02. And since we're making a confidence interval, that gets split up. So how much is in each tail? Cool. So I'm going to look up 0.01, and I'm going to look up, that's insane. It's so crazy it might work. Just so crazy. It might work. Don't laugh too much at my stupid joke. That'll encourage me to make it work. So you look at 0.01, 0.99, they're like the second to last and second columns, right? So we go down to 50. I'm looking the wrong way. That one's moving. All right, there you go. That's going to freak me out. So go down to 50 over there. So if I look at the second column in, this is going to be chi-square small, because that's where the small ones are. So 29.707. chi-square small. What's chi-square big? Look in the same row. Degrees of freedom is 50. Weird things are happening out there. Go all the way out to the second to last column. 76.154. You guys with me?
Yes.
Everybody? Good. That's more than normal. I like that. 76.154. Again, this acts just like, I know I keep saying this, I don't care. Negative 2.575 up to 2.575. That's the number we're used to. Right? Or 2.576. It acts, it does the same job. So now all I got to do is throw everything in there. That's all I got to do. Just throw everything in there. We got n minus 1 times 8.019 squared divided by chi-square big dude. So the tops are the same for both, which is kind of nice. Divided by chi-square small dude. And it's so damn easy to make a mistake of squaring this because you're like, it's a square there, but that's the symbol is chi-square. It's the symbol. That's the number you're finding. Don't square it on top of that. You're going to get weird answers. I don't know why I didn't. I mean, everything numbers except for this. So what's n minus 1? 50. 50. All right. No, I don't want to see a movie. So if I do, see if I remember 50 times, I don't trust me. 8.019 squared. Divided by 76?
0.14.
0.14? 154?
Yes.
Okay. I get that. Good Lord. All right, is everybody with me here? You guys with me? I get for this, for the lower bound for my variance, I get 42.22 basically. And then this, I could just do this. I could just hit second. So divided by 20 something or other, right? 29.707. 707?
Yep.
108. 1231. Now what is it the confidence interval for right now? Varies. And I want the one for standard deviation, so I just take square roots. So if I square root bigger dude, I get 10.4 blah blah blah. And if I square root the other guy, that's enough of that. Okay, I'll get 6.497. Okay, so I get the real standard deviation is 6.498 up to 10.403. And how do you think you would word? Oh yes. Oh yes. How would you word your conclusion here? We are. Beautiful. I love it. I love it. And of course, people that aren't sure, you're like, what does everybody say? So we are 98% sure, confident that 6.498 years to 10.903 years, or whatever that is for, contains the true standard deviation of dogs' lifespans. I mean, it's exactly the same wording as we did for the other confidence intervals. Why? Because it's just a freaking confidence interval. They all act the same. They all tell you the same thing. How do you get to them is different. But once I'm there, they tell me the same thing. Maybe. Let me write it down. So we are 98% confident that the interval How many years? 10 points. I think it's 4 or 9.
What's it?
Contains the truth.
We said we.
Same exact wording we've used forever. Yeah, ever since we learned opposite.
I wasn't on this platform.
Restless class. Everybody got a practice one?
Alright, see you later, man.
Alright. Yeah, I'm not going to keep you guys anymore. You're all like caged animals.
Yeah.
Go out to the world. So I have the answer key for this next time. Don't forget also about the other reviews in the Mass Study Center. It's not in the Mass Study Center, but if you want to.
Your odds.
Alright.
Oh yeah, it's cool. My grades aren't terrible. You're your grade.
Second.
I did good on the test. Wait, did I miss any tests? No. I don't think I missed any tests.
That's great.
Oh, I don't know, man. I'm just saying. I'm good at this. You're doing this like forever. What's my math? I had it they were fine. And my fucking after having it
The day of the final, I'm just going to put you
It's like the first. Yeah, it's smart. It was the first time I sparred and like, and I am incredibly fast. I lost my weight. I lost like 20 pounds within that time.
I know it's almost in the sign
Somehow. You do. It's very, very worth it.
Oh, did I just give this back? I'll give it back to you. Okay. So on Wednesday, I'm going to have scheduled finals. So one of the days of my final.
Alright, you too.
You guys final is on the. So then the final I'm giving. Yeah. So just remind me once you have my schedule. Hey, got it right. Yes. That's your current area.
So, they want to get the position more or less. Oh, Tom, like this.
You didn't get that sheet?
Yeah, that's still right on it. If you, for example, that I
Okay, yeah. Because I'm not going to know those numbers. Okay. Meet me over in my office.